Alright, good morning everybody. Welcome to the date of birth circuit assignment. Now, if you're watching this video, you may have either missed it on the first day, or we're doing things asynchronously, or I've just decided that I'm not going to lecture on this one again, because hopefully this video answers all the questions. Either way, let's get started. So, the gist of this assignment is that you've been tasked with creating a circuit that will display the digits of your date of birth as you flip your way through them. Now, the way we're going to flip your way through the digits of your date of birth is you're going to take 3 switches, and when all those switches are at 0, it'll show the first digit of your date of birth. Now, I currently allow you to do any 8-letter word instead of an 8-digit date of birth. Now, if you are doing your date of birth, for instance, this assignment would look a little bit more like what I'm going to do here instead of the word I'm spelling, which I'm spelling the word Atlantis, because my wife and I have been watching a lot of Stargate Atlantis recently. So, let's say my birth date was 07-16-92, right? Now, I could go through and I could do the date of birth. We're going to put a dash between the month, a dash between the days, and then we're going to do 2 digits of the year. Honestly, I like doing letters a little bit more. I think it's a little more fun to write out a word. It's totally your call which you do. If you spell a word or you do your date of birth, the key is the word must be 8 letters long, and they have to be unique characters, so you can't just be like, eee! Sorry. Now, once you have your word written out that you want to do, what you're going to do is you're going to then translate it into the language of a 7-segment display. That is, you're going to take the letter A, in my case, and you're going to figure out which segments on your 7-segment display you would need to light up to get a shape that kind of represents an A. You can Google this if you're uncertain of how to translate a letter onto a 7-segment display. Remember, those displays have 7 individual segments, A, B, C, D, E, F, and G, that we can use to light up letters, right? Each of those segments is essentially an LED. If we are using our common cathode ones, we'll just need to give them a 1 in order to turn them on. So you should plan around using common cathode logic. That is, a 1 on a segment turns it on because they all have a shared grounding pin. So, here, I'm going to start out with my letter A. A is the first letter that I'm going to display if I'm spelling out Atlantis, so that goes in my zeros area. Then T is the next letter. I'll look and I'll figure out, okay, I need to light segment F, segment E, segment D, and segment G to make a T-like shape. It's a lowercase t. Some people will do the uppercase T by doing segment A on top and then F and T on the sides. I just don't think it looks too much like a T to me, so I try to go for a lowercase t shape. You're going to find you sometimes mix cases in order to get letters to look right. I don't really like a lowercase a on here, so what I've done down here is I'm just using an uppercase A for all of the A's in my word. Now, if we come over here, when I have X, Y, and Z at a 0, then I need to be spelling out, I need to have my segments display an A for Atlantis. So, when all those are 0, I'm going to look at this. I need to do the A for Atlantis. Segment A is going to be on if I'm doing my A for Atlantis. Segment B is going to be on if I'm doing that A. Segment C, also on. D at the bottom, however, is going to be off because I don't want to light that one up. The remaining 3 segments are always on in an A. So you'll notice A has all but 1 segment turned on. Alright, that's my first step. Now you might want to be like, alright, let's move to the next step. We can't quite do that. What we're essentially doing here is we are making 7 separate truth tables, 1 for each segment of our display. We'll then be building 7 circuits, 1 for each segment of our display, based on that truth table. It will drive what we're doing from here on out. So, I may have taken care of 1 letter, but I need to take care of every single letter before I can start building a circuit. So let's take care of that. For T, A is going to be a 0. This is a good place to fast forward if you're watching from home. B and C are going to be zeros. Then I'm going to have D D, E, F, and G all on. For an L, well, an L and an I are so similar that we sometimes just pick which side we put them on, to be honest. And I just usually put my L's on the left, actually, and my I's on the right. I had those flipped around originally when I made this. Sometimes an I is just a lowercase, so just one, like that, and that can make it a little easier. All right, if I'm doing my L, I'll notice that only F and E are on, so everything else could be 0. If I'm doing an A, I can just repeat my truth table or my segments from my first A. It's nice when you have letters that repeat. And I'm going to notice that it is only segment C, segment E, and segment G that are on. So there's G, there's E, there's C. Next one up is T. So you can do segment T the same way you did it before, which is kind of nice, right? You just go back and copy what you did for the first one. For my I decided I was going to do that lowercase I in the lower right. Therefore, it's just going to be a 1 in the C column, 0s everywhere else. My last one is an S for Atlantis. Segment A is going to be on. Segment B is going to be off. Segment C is going to be on. Segment D is going to be on. Ooh, segment E is going to be off. And then the last two segments are going to be on, F and G. Alright. Now, we have made a truth table for each segment of our 7-segment display by looking at each letter and saying which segments would have to be turned on for that letter. Our next step is we need to create a circuit for each segment of our 7-segment display. Now, you could go through and you could write out the unsimplified logic expression for every single segment of your display, right? I could go through and say, okay, well, this is x naught, y naught, z plus, I would have to say plus x naught, y, z plus x, y, z. It's actually not that bad for segment A because it's only used in 3 places. But this is a great chance for us to use our K-mapping abilities that we built earlier in the year. That's going to let us shrink our circuit down and save ourselves some time when we get to our build. You can use Boolean algebra, you can use the logic converter in multisim, or you can use the K-map. I will tell you that if we have an inclement weather day, the day you're watching this video, the expectation is that you use the K-map rather than just pause here, and you complete the K-map for each of your segments so that you come to class ready to start designing circuits next week. It's actually on Thursday, excuse me. Alright, so anyway, let's do the K-map for segment A. Right, we're just going to be doing segment A right here. And so all we have to do to build our K-maps again is just say, okay, well here, x is 0, y is 0, z is 0. Alright, so when x, y, and z are all zeros, I see A as a 1. Well now, when I'm building my K-maps, I like to just find my 1s with a segment like A. Because for instance, A had a 1 at 0, 0, 0. A only had 2 other 1s, right? It had a 1 at 0, 1, 1. So I'll go here and I'll look for, okay, x is 0. I need the other 2 to be 1s. Alright, there's 0, 1, 1. And then the last place I need to have that one is all the way down here at 1, 1, 1. So I'm going to have it over here, right there. I double check always. I see I have 1, 2, 3 1s in my K-map. I look over here and in my truth table I have 1, 2, 3 1s. That means I copied them all over. I could have made a mistake still, obviously, and put them in the wrong place, but it's just good to double check yourself since this is a big build, and you want everything to work on the first go. I'll fill the zeros in for the remaining parts of that truth table, and then I'll go about and circle my sections of the truth table. Right there, I notice that that 1 is all by itself. There's no adjacent 1s to help it out, so I just have to circle it by itself. Right there, however, I can get a grouping of 2, and that's going to at least help me create a slightly smaller logic expression for segment A. Because segment A, I like to say FA, right? The function that describes how segment A works is x naught, y naught, z naught, all of them at 0. And then down here we can see x changed right there. And so we can just say plus y, z, because we can get rid of the input that has changed within the K-map. The x was both 1 and 0 within that K-map, so it can go away. All right, the next step we would have after that is to go about designing our circuit. Now, if you happen to have multisim with you right now because you're working from the classroom or you just happen to have found a way to get it at home, you can go on in and you can use your logic converter, punch that into your logic converter and say, hey, generate my circuit, right? I mean, it takes a second. But like, let's say you're working at home and you're trying to get this done. Well, it's not too bad. You can start by drawing everything out. I like to start by being like, all right, here's power, here's ground. Here are my 3 switches. Okay, remember, the name for a switch in multisim is SPDT. You could build this in multisim live, which isn't a bad idea. You're going to have to build this thing physically, so the more you have done when we're in person, the faster you'll be able to go, and the easier that build is going to be. So here's switch Z, right? We're going to give it power. We're going to give it ground. So that'll be switch X. We'll go in order. Then here's switch Y. Give that power and ground. And then here's switch Z. We'll give that power and ground. I know you might be thinking, mate, why aren't you building this in multisim? You're here, you have all the resources. Well, because honestly, if I'm going to ask you to draw them out by hand, I don't mind doing a few of them. They really don't take too long, do they? Right, here's switch X, Y, Z. I'm just moving my labels so I can draw my connectors coming off of there. So there are my 3 switches coming out. And now, what a lot of people like to do when they build this assignment in multisim, and so I just do it when I draw it, is I actually create a bus by hitting Control J and creating those lines for each segment that run up and down. Now, since I'm drawing on here, I'm going to change the color for each switch to help you keep track of what I'm doing. This isn't a bad plan in multisim because that's also going to allow you to keep track of your wires. It takes a lot of work in multisim. It's just nice when it gets time to print and then build. Use color coded a few things. X is going to be blue. Y is going to be this marker someone colored all over black with earlier. So we're going to have to pick a different color. Aren't you glad you can turn me to 2 times speed on YouTube? Here's Y. Kind of this pale purple color. And then Z will be this kind of pink color. Spring, these colors feel appropriate for spring. That's Z. That's Y. Over here we've got X in blue. Again, just using colors to kind of keep track of where we're going and what we're doing. So the first thing I need to do is I need to build my logic expression for segment A. The way I'll do that is I'm just going to look and I'm going to see, oh, I have X naught, Y naught, Z naught. That means I'm going to need 3 inverters to start this circuit. There we go, 3 inverters. I also notice that these are all connected together with AND gates. So I see that I have these 2 right here, that'll be an AND between them, and these 2 right here, that'll be an AND between them. That means I need 2 AND gates to represent essentially the multiplication there. So we just reuse those symbols. Last thing is I know I'm going to need an OR gate to connect the 2 expressions, the 2 min terms of this logic expression. And then I know I'm going to need an AND gate to connect Y and Z. Alright, Alright, now let's go about creating our circuit. First thing we need is x naught, so I'll come back here and I'll grab x from right there. That'll produce x naught right there. I'll go and grab y off of this bus. That produces y naught right there. The last thing I'm going to do is bring z over and get z naught right there. Feed the outputs of those into my AOI logic gates. And from there I get x naught, y naught, which I'll feed into that next AND gate and bring z naught in to produce x naught, y naught, z naught, which gets connected to our OR gate right here. So the output of that will be x naught, y naught, z naught, or the other thing we add in, which we will create by connecting y and z together with an AND gate. So we'll come on over here, we'll grab y. Maybe saw right there, the color coding already saved me from drawing a wrong line without thinking. Because I was coming at this and I was almost going to grab the wrong color. Would have been a mistake that would have followed me throughout my circuit. Would have been kind of a problem. So here I have gotten my segment Y and my segment Z, for my switch Z inputs. Over here, that created my YZ section, and then that will be forward on to have YZ over here. When you went to the breadboard to build this, you would then bring this wire over to your 7-segment display, which has a common cathode, that is a shared ground pin. And you remember there's one on either side. There's A, there's B, there's C, there's D, there's E, there's F, there's segment G. And now we'd go look at it and we might say, oh, hey, look, on the data sheet I see segment A is right there. And you bring your switch, your wire down and you click it in right there. Then you're going to draw up the circuit for segment B. You'll do the circuit for segment B again by K-mapping this right here. And then you'll be like, okay, this is K-mapped. By plugging it in there, it'll give you a reduced logic expression. You'll go and you'll take that reduced logic expression and you'll build a circuit, and that circuit will get connected in for segment B. Once you've got all that done, you should have 7 circuits driving your 7-segment display. Now, the last thing I want to point out, and I don't have any repetition in my segments. I don't see any of my segments here that have the same truth table for them, right? No matter which segment, all of mine are a little different. However, some people are going to notice that sometimes 2 segments will have identical truth tables. If you have 2 segments that have identical truth tables, then you only need to build one circuit for those 2 segments and then just wire that up into that circuit to both the segments. If you have questions about that part, make sure you drop me an email and ask me what's up. In general though, this is what you'll be building, and you should be doing this much in about 1 class period. It's not a lot if it's just sitting down and doing some focused work, because we've learned how to do all of these skills so far. We learned how to use 7-segment displays earlier in the year. We learned how to create a truth table for a specific behavior. Then all we're adding in this assignment is, well, we're using the same 3 inputs to create 7 truth tables instead of just 1. You've worked with those 7 segs a bunch, and now you've also used K-maps to reduce a truth table and create a reduced logic expression. And you've gone from logic expressions to creating circuits that you could then put into multi-sim and design on a breadboard and see if it actually works, which you'll be doing once you're done with your design phase. Anyway, again, email me if you've got any questions.